Hello and welcome everybody to the course Crystal Engineering Chemistry Beyond the Molecule. Well, during this lecture series you heard so many things about intermolecular interaction, how to design desired crystals by using syntons. We learned so many things about hydrogen bonds, halogen bonds and so on. And in the last videos we talk about crystallization methods, different crystallization methods, techniques, tricks, how to tune crystallization processes. And the importance of such things, tuning crystallization processes, is well established in the pharmaceutical industry by development of APIs, so active pharmaceutical ingredients. And so today we will talk about applications of crystallization techniques and the usage of different techniques and how to tune these techniques in the pharmaceutical industry, especially pharmaceutical polymorph and co-crystal screening. This topic has a really great impact and is increasing in the last years. Was a very nicely contribution in chemical communication of Savarot group, yes, and very nicely shown starting from the molecules and ending in medicines and the different ways, for example, salts, development of salts, or the development of co-crystals. Pharmaceutical co-crystals can enable better medicines by improving physiochemical properties of drug substance in a manner that is not always readily achieved when using traditional approaches to pharmaceutical materials. Very interesting contribution. Well, okay, first question is why? Why is it important to make a polymorph screening, a co-crystal screening? You remember we talked about polymorphism, and we have seen that different polymorphs can have different properties, physical properties and chemical properties, solubility, bioavailability, something like this. Yeah. And well, here are some properties, not only solubility, drying, flow, tableting, shelf life, and well, this is the most important, bioavailability. And on the other side, if you're looking into the patent view, the problem is that always the mixture of polymorph is a mixture of two different crystal structures. Yeah? So each polymorph has its own properties, chemical and crystallographic properties, and this is still enough that each polymorph can be patented. Yes. And well, this is a really very important aim to avoid each suitable polymorphs, or to check for each suitable polymorph, but and when you can patent each polymorph which have maybe suitable properties. So the aim is two things. The aim is not only to look as much as possible polymorphs, the aim is first to improve the property, optimal form of this drug, enhance physical, chemical and biopharmaceutical properties. And for example, if the aim is looking for a more water-soluble form Well, first they look for each possible solid, as many solid form as possible, and then have a look. Then have a look for each of its possible forms, each solid. Have a look on the physical, physicochemical, and biopharmaceutical properties, and check if maybe a better properties, a form with better properties, enhanced properties, was obtained. We can distinguish between two phases in the development process. The early phase, we're looking for, how shall I say, not a poor form, we're looking for hydrates, solvates, we're looking at amorphous materials, for example, amorphous crystals, amorphous materials have not the same properties like crystalline product. Each of these classes, this is not only one compound, this is classes of hydrates, classes of solvates, are relevant for patent, each of them. No? And in the second phase, or you can say in the later phase of the development process, we're looking for co-former, not conformer, co-former. We're looking if there maybe polymers can be used in the crystallization process. We are looking for maybe it's possible to develop a co-crystal which is formed by two APIs, by two drugs, something like this. No? This is the second phase. First, looking always hydrate solvates, and then looking in the always field of co-crystals and polymorphs. So let's have a look on the polymorph screening. Well, the most typical polymorph screening is solvent. So we can say we have two most typical forms. One is solvent, the second is mechanochemistry. We will come to this point a little bit later, but first talking about solvent-based. And well, you see it is a wide-ranging screening with many different parameters. Okay, now think by yourself. Each of you has experience in the lab, and what are you doing if you want to get looking for a polymorph of your synthesized product? Now, what are you doing? Which parameters you can change? So for example, you have a compound which crystallized from, I don't know, from ethanol. Yes? Okay? And now how can you try, how can you study the crystallization behavior of your compound in solvent? Which parameters can you change? First, look to the heating and cooling rates. Yes, you have your compound, for example, dissolved in ethanol. And what happens if you heat your mixture very slowly until your product is dissolved? And what happens if you change the cooling rate from the solution? Very quickly, long time, and so on. Long time, I'm talking about days, not minutes. Days, sometimes weeks. Supersaturation. You have your compound ethanol solution. what is the amount of your product in this solution. You remember, we talk about solubility and supersaturation curves, lines. We talk about metastable zones. A lot of these drugs are soluble in water. This is important. So this is one aim of APIs, that they are soluble in water. Not all of them are soluble in water, but this is important because if you have this is soluble in water, you have a higher bioavailability, and higher bioavailability is one parameter which should be improved. And one parameter is tuning the pH value of your solution. Next parameter is evaporation rates, quickly, slow, not only with two poles, always each step by step. Okay, and then addition rate in antisolvent crystallization. And once again, keep in mind the importance of metastable zone. At which point you will add how much antisolvent. You see, this is always parameter can be tuned. And now thinking by yourself, are you doing all this? Are you tune all these parameters if you're looking by your own in the lab, if you handle and crystallize anything? Yes? So maybe next time you can think about if you crystallize something from solution. Another point is very often in the pharmaceutical industry or the general development of APIs, you are using slurry techniques. I will come back on a little bit later. This is the suspension of your API or substance in a solvent, and you're only stirring. You see a long time, 2 days, 2 weeks. And very often this is very helpful. You see it as, for example, here's a study with around about 30 early developed drugs, and around about 25% of the screened compounds, yes, a more stable compound was found by using this technique. And later on, a more stable was not found. So the slurry technique is a very helpful technique in polymorph screening. We talk about several times of importance of intermolecular interaction, of interactions not only between two components in a co-crystal, also of the importance of interaction of a material, your product, and your solvents. So effect of solvent-solute interaction. And this is very important if you're talking about nucleation process, so the first step in the crystallization process. This is interesting if you look to the crystal grow, in which direction of the cell axis, for example, your crystals grow. This is strongly depends of this exactly with interaction solvent-solute. And solvent-solute interaction have an influence on solvent-mediated polymorph transformations. So in the solvent, switching from one polymorph to the other polymorph. And so it is very important to look which solvent we are using, going back by yourself, thinking by yourself what you are using in the lab normally, so ethanol, ether, THF, toluene, aromatics, alkane, something like this. No? So this is a very crude classification. If you really want to check, really in detail want to check the polymorphic behavior, crystallization behavior of your product, you should look in the database of solvents. And this is one of normally there's a database around about 100 solvents, and they are distinguished or categorized in 15 classes. And classes is based on the parameter like hydrogen bond, donor, acceptor properties, the dipole moment, dielectric constants, viscosity, surface tensions, for example. These are only some of them parameters, yes. Yeah. So this is not only still enough to say, well, I tried in ether to crystallize my compound, now I change to, I don't know, ethanol. Okay, this is one way, and sometimes very often it works very well. But if you really want to figure out in detail the crystallization process and figure out that you really have checked the polymorphic behavior of your crystals, of your compounds, when it is necessary to look in detail on exactly such things, you know, the interaction, solute, solvents, and in detail which solvents can you use. You see, so many things, parameters should be keep in mind if you're looking for crystallization behavior from solution. Now have a look on polymorph screening, so mechanochemistry, so dry methods. No? Why this is interesting? Well, first, thermal activation is very interesting. You want to study, you want to know at which point, for example, your compound melt, crystallize. When we are talking about energies, no? You want really to study if there are, for example, different crystallization points, melting points, yes, at which temperature. And you want to know, you want to study in depth sublimation, temperature and energy. And dehydration of a solvent, if you hydrate, what happens? Yes, so at what point the temperature, the dehydration process starts, and what end, what happens with your product. Yes. This is typical diagram, yes. Yeah. We have energy here, and we have a temperature here, and you see first you have a crystallization, and at higher temperature melting. So this is also a very crude description. In this case we are talking about DSC, thermoanalytical technique, temperature-induced change in the properties of sample materials. And this is interesting for you if you want to learn more about your product. You want to learn, for example, is there a phase, is there in a glass phase, glass transition temperature, for example. You want to learn more, is there a switch transformation from amorphous phase to a crystalline phase? And coming back to polymorph screening, is there a point, a transition point, phase transition of polymorphic substance. So you see this method is standard method. Standard method in solid characterization in organic chemistry. Yeah. If you want really to check, to learn more about your compound regarding crystallization and melting process. Well, I will show. First of all, we are talking about energy. Yes, so we are talking about exothermic processes and endothermic processes. Once again, you use the energy, so thermodynamic, exothermic and thermodynamic, endothermic processes. Exothermic processes are, for example, oxidation processes, crystallization, polymorphic conversion to a low energy modification. And on the other side, if you're talking about endothermic processes, then you're talking about melting, sublimation, and in the other direction, polymorphic transformation to higher energy. This is interesting in anisotropic systems when we go with both sides. Well, and not only characterization and learning more about the crystallization behavior, you can also use this technique in screening tasks. For example, we're starting from physical mixture of two compounds and looking what happens. Here are two different examples. Both are with amide, crystallized with salicylamide, and in this case with benzamide. Both starting with a physical mixture, 1:1 ratio. So, and what happens, you see the difference. And one here on the right side, we have only one peak, and we have, you see here, two peaks. First, both, this was the same, this is eutectic point, formation of eutectic melting point of the two physical compounds. And on the right side, that's all, nothing happens. On the left examples, if you're heating on, well, something happens. There's an endothermic point, been observed. This is the co-crystal formation, and you see the co-crystal melting point. In this case, nothing. So in this case, you have a co-crystal. In this case, nothing happens. So you see, this technique is helpful to check if co-crystal can be formed or not, or are formed or not. Next point, in the polymorph or general development of APIs is salt screening. Salt screening, so not co-crystal screening, but salt screening. This is important always if you have a drug with extremely poor solubility and poor bioavailability. When you can switch, or you often use a switch to salt, and in this case you have a higher solubility and mostly higher stability of your API. And this is very common in the development of drugs. You see it here, more than 50% of all marked pharmaceutical drugs are salt in USA. What are you doing to obtain a salt? You remember, the salt formation strongly depends on the proton transfer of the two compounds. yes, 2 compounds. And you can vary with this very nice equation here, the delta pKa, so pKa of the acid minus the protonated pKa of the base. And I have shown you exactly this equation in a video before. Here is very nice. Here I've shown you in the case of fluorocytosine. If you crystallize fluorocytosine in the presence of oxalic acid, when you will get a salt, and in the case of succinic acid, this one here, you will get a co-crystals. And if you look to exactly this equation, so delta pKa, you will see in the case of a co-crystal, you have a much more lower delta pKa, around about 0.9. In the case of a salt, you have around about 2. But as I said, this is very important. This is a thumb rule. This is a thumb rule, and a lot of exceptions are well known. But this rule does not fit. Yeah? But anyway, if you have a really high delta pKa, when you should have, it should be possible to get a salt. Once again, now we want screening. We want to screen salt formation, crystallization of the salt from solution. And once again, similar like the crystallization of solution, we are thinking about concentration. So it's not still enough to take both compounds, ratio 1:1, put it in a solvent and looking what happens. Sometimes that's still enough. But when you must tune and check if some other compounds could be crystallized. So this is once again concentration of the solution. Looking precipitation from a saturated solution, yes, the ratio, for example, the amount, the yield. Once again, we are talking about cooling and evaporation methods, and once again, we are talking slurry conversion. So with slurry conversion, well, it was not still common in our labs, but in general, if you want to improve or check or whatever you want for more stable compounds, one is slurry conversion is really becomes more and more important in the always field of material improvement. Now, if you look to all these parameters which could be tuned, question is, what is the most successful method in polymorphic screening or not polymorphic screening, in salt screening from solution? And there's a very nice study in where he looked to all this development and all the studies of salt screening of APIs, and well, this is the result. The preferred choice, yes, in the salt screening from solution is saturated solution methods. The second point, the second preferred choice is cooling evaporating crystallization. This, you see the parameters suggested in a situation where the APIs had the potential to oil out. And the third one, as I said, is coming up really in attention, the in situ slurry conversion method. Well, an alternative method to get a salt is trying to get salts by using mechanochemical methods. Yes, And well, we talk about this type: neat grinding, solvent drop grinding, liquid assisted grinding. And similar to always solvents based techniques, the question is what is the most effective techniques. That's very nicely studied. And here is a study about getting crystals of these two compounds, yes, and in the presence of 7 different carboxylic acids. If you use neat grinding, you will get, or they get, 4 new salts. If I use liquid assisted grinding, we got additionally 9 salts. So these are some techniques to get salts from mechanochemical grinding. And you remember, I've shown you how you can use DC to learn more about the crystallization process, melting process of your compound, and how you can use DC to check if maybe a co-crystal is formed or not. Another method to monitor and to have a look if something happens between 2 compounds is uses of hot stage microscopy. It's very easy. You need only a microscope. It is heated here, you see it in the stage, and then you can very nicely observe what happens or not. This is a typical picture. This is compound A, this is compound B, and well, when the stage is heated and you see something happens here in the middle, and what's going on. So this was in contact area around about 200 degrees. As I said, the 2 compounds, and this here, the C, region C, this is the region a new compound entity is formed. Yes. And what you see also is here in the region D, the borderline to region B, is that an eutectic mixture of C and B start to melt. So hot stage microscopy and DC are one of the first experiments if you want to check if 2 compounds are able to form a co-crystal. Another point we several times talk about is the slurry technique. This is very nicely. The compounds are suspended in a solvent, and this is very important. It is suspended, but not totally suspended. There's a partial dissolution of your compounds, and this partial dissolution maybe is the reason that a nucleation can be observed, occur. And in this case, the API and co-former then will form a new co-crystal by solution-mediated phase transformation. Yes. Well, slurry techniques, this is the method if you really want to get the most thermodynamically stable compound. And well, we have a technique was the mechanochemical grinding, and question once again how effective is such grinding techniques. If you look, for example, the co-crystal grinding of caffeine and succinic acid, if you make solution-based synthesis, yes, different solvents, when you will get 4 co-crystals. if you need grinding with both components by itself, you will get 16 co-crystals. And if you use liquid assisted grinding, you will get 18 co-crystals. And you remember a similar slide I've shown you some minutes before. And so in general, if you look to several studies, when you can summarize that liquid assisted grinding is the most popular method in this, the whole grinding, mechochemical grinding methods, no? Liquid assisted grinding. I think with values, with results are really impressive. There's another method. This is called, if you're looking for co-crystal screening, this is called co-crystal cocktail methods. For example, you mix your compound, your API, with 4 co-former, and all together they're grinded in a ball milling. Well, be careful, this is sometimes a nightmare, but on the other side, we can, when we can check it by Pauli diffraction, when you can see if something happens or not. If something happens, then this could be information for you, for example, for you regarding are there some interesting interactions, intermolecular interactions, and second information about hierarchies, yes, hierarchies of the bonding situation. But so from my point of view, this is only first identification hint if something happens or not. This is one of the first preliminary steps in the co-crystal screening, not more. Very often development of co-crystals or polymorph, co-crystal is in try and error way. And one suitable pathway beside this try and error is to look to thermodynamic relationship of your compounds, and by using phase diagrams. One is the binary phase diagram, I will show you here. You have a temperature, and what here, temperature composition map. This is your composition, proline and fumaric acid, in weight percent, the temperature, when you can see, observe at bit temperature your compound melt and crystallize, and you see the points of eutectic composition. In this case, you have 2 very closely eutectic composition around the co-crystallism composition, and this region, this is the region of your co-crystal formation. This is binary phase diagram. More interesting, much more difficult, is ternary phase diagram. In this case, or once again, in this case, we are looking only to the 2 solids. Yes, your compound and your co-former building a co-crystal. In this case, we are looking to the compound, co-former, and the solvent. Yeah, and this is interesting. Once again, an alternate approach to try and error. Interesting to map out the critical region, which region of a ratio of a compound, a co-crystal, and the solvents, which is the critical region in which the co-crystal is formed. Yes. And this is a typical ternary phase diagram. Well, have a look. We have these three partners, I would say: the drug, the co-former, and the solvent. Yes. And similar like a binary phase diagram, this is the composition here. Yes. And what you see, a lot of zones, 1, 2, 3, 4, 5, 6 zones. Yes. If you're looking only to the lines here, no? This is one zone, this is the second zone, so this is the first, the second, always looking to the bold lines. Yeah. Okay. And you see dotted lines and some points. Well, now have a look. What is it? First, what we see is two eutectic points. The solution is saturated with these two solid phases. These are the two eutectic points. As I said, we have 6 zones. And the co-crystal solubility curve, co-crystal is between these two eutectic points. This is very similar if you compare it here with the binary. Very similar here. Okay. So now have a look on these different zones. This is here the zone 1. Yes, this is unsaturated solution of drug and co-former. Unsaturated. And what we see is here the line A here, to E1, to the eutectic point with the solubility curve of the drug, and with here from B to E2, this is the solubility curve of the co-former. Okay. Zone 2, this is 1. This one here, this zone. This is the drug of a stable zone phase of a drug. See it here. Zone 4, this is the stable form of a co-former. Zone 3, this is your desired zone. This zone here. If you want to get a co-crystal, your aim is to reach this zone. You see it here? Yes. And this is important. Figure out this zone. This is better than try and error. All the different mixtures and ratios which are possible. Okay? Zone 5 and 6, also interesting. This is invariant regions called, and with a mixture of a co-crystal and drug, or co-crystal and co-former. So with this slide I will end this presentation. And I think you have seen how difficult it is to really figure out the most successful conditions in polymorphic salt and co-crystal screening. And hopefully you can use this technique not only in the crystal engineering world technique. Hopefully you can use this technique in your own projects in the lab.